For decades, scientists believed Europa's ocean was too buried to tell us anything. Too much ice. They may have been wrong. NASA's JWST found carbon dioxide concentrated in places where Europa's surface appears to have recently broken apart. Which means the ocean below may not be as isolated as anyone thought. And if that is true, then what NASA may have found at the bottom of Europa's ocean changes everything. So, let's go down there. Now here is where things get really interesting. And here is where NASA delivers on the title of this video. In September 2023, two independent teams of scientists published results using data from NASA's James Webb Space Telescope. They had identified carbon dioxide on Europa's icy surface. Carbon dioxide had been detected there before, but the source was unknown. Was it delivered by meteorites, produced on the surface by radiation, or did it come from inside the moon, from the ocean? Webb provided the answer. The carbon dioxide was concentrated in a region called Terra Regio, a geologically young area of chaos terrain where the surface ice has been disrupted, and there has likely been an exchange of material between the subsurface ocean and the surface above. Previous observations from the Hubble Space Telescope had already shown evidence for ocean-derived salt in Terra Regio. And now, carbon dioxide was heavily concentrated there as well. The conclusion was compelling. The carbon probably has its ultimate origin in the internal ocean. One of the lead researchers put it plainly. Scientists have been debating how much Europa's ocean connects to its surface. This finding suggests we may be able to learn basic things about the ocean's composition even before we drill through the ice. Carbon dioxide is not stable on Europa's surface. It breaks down under radiation. That means it had to be supplied on a geologically recent timescale. Something is actively bringing material up from the ocean to the surface. Something is connecting the two. On Earth, carbon is the backbone of biology. Every living organism is built from carbon-based molecules. Understanding the chemistry of Europa's ocean is fundamental to determining whether it could support life. And now there is observational evidence that the carbon on Europa's surface came from the ocean. That is not a trivial thing. Europa is also constantly exposed to intense radiation from Jupiter. That radiation splits apart water molecules on the surface. The hydrogen floats away, but much of the oxygen stays behind. Oxygen is highly reactive. If it somehow makes its way down through the ice to the ocean, it could react with chemicals in the water to provide energy for microbial life. The very thing that makes Europa's surface lethal to life may also be creating the chemical ingredients that life needs below the ice. But carbon was not the only discovery. In January 2026, a researcher at NASA's Jet Propulsion Laboratory published a study reporting the first detection of nitrogen on Europa ever. Nitrogen, like carbon, hydrogen, and oxygen, is one of the four elements that make up 98% of all living matter on Earth. Its detection was a significant moment. It was found in the form of ammonia-bearing compounds, hidden in decades-old data from NASA's Galileo spacecraft. The signal appeared near fractures and young geological features on the moon's surface, the same kinds of areas where liquid water from the subsurface would be expected to rise. Something had brought it up from below, and recently, ammonia matters for three important reasons. First, as the first detection of any nitrogen-bearing compound on Europa, it adds a crucial piece to the habitability puzzle. Life as we know it cannot exist without nitrogen. Second, ammonia acts as a potent natural antifreeze. It can lower the freezing point of water by up to 100 degrees. Its presence means the ocean beneath the ice could be even more extensive and chemically complex than models have suggested. Third, ammonia is highly unstable in Europa's harsh radiation environment. It is destroyed within less than 1 million years of exposure. The fact that it is still detectable means it was placed there recently on geological timescales. Something active brought it up from below, most likely through the slow eruption of liquid water from subsurface reservoirs. And here is the thread that ties it all together. Same fractures and chaos terrain where ammonia was detected are the same areas where carbon dioxide was found, the same geologically young surfaces, the same evidence of ongoing exchange between the ocean and the world above. Material is coming up, and it is carrying the molecular ingredients that life requires. So what do we actually know about this ocean? Scientists believe Europa's global ocean sits beneath a thick shell of ice and above a rocky seafloor. On top, the icy crust. Below that, a vast liquid ocean. At the very bottom, a rocky mantle surrounding an iron core. Europa is slightly smaller than Earth's moon, but it likely holds far more water than our entire planet. An ocean estimated to cover the entire moon to a depth of up to 100 kilometers. The deepest point in Earth's ocean reaches about 11 kilometers. Europa's ocean may be 9 times deeper than that, encircling the entire moon. To understand what's happening inside Europa, you need a picture of its layers. At the very top is the ice shell. This is the surface everyone sees in photographs, white and cracked, streaked with rust-colored lines. For years, scientists argued about how thick this shell was. Some models suggested it was less than a kilometer deep in places. Others suggested it was dozens of kilometers thick. The debate matters enormously, because the thickness of the ice determines how easily material can move between the surface and the ocean below. In January 2026, new data from NASA's Juno spacecraft provided the first measurement precise enough to settle part of that argument. During a close flyby of Europa in 2022, one that brought the spacecraft within about 360 kilometers of the surface, Juno's microwave radiometer measured temperatures through the ice at various depths. The result was a shell averaging approximately 29 kilometers thick in the region observed. That is thick. Much thicker than some earlier models had proposed. Below the ice shell lies the ocean. Scientists estimate it could be up to 100 kilometers deep. If that figure is accurate, it would make Europa's ocean more than 10 times deeper than the average depth of Earth's oceans. And because liquid water expands the possibilities of chemistry in ways that no other substance does, the sheer volume of that ocean is significant. Whatever chemistry is happening in there is happening across an enormous amount of space. Below the ocean lies the rocky seafloor, and beneath that, the rocky mantle and a metallic core. This is where the story becomes more complicated, because the interior of a world, its heat, its geology, its chemistry, is what determines whether an ocean can support life. And what the science says about Europa's interior is not straightforward. On one hand, there are reasons for optimism. On the other hand, there are reasons for significant doubt. Both sets of reasons come from serious, peer-reviewed science. And as of today, neither side has definitively won the argument. Life as we know it requires 3 things. It needs liquid water. It needs chemistry, the right combination of elements and molecules. And it needs energy. Europa clearly has the water. The chemistry question is something we will come back to, but the energy question is the one that has divided scientists most sharply. On Earth, most life ultimately traces its energy back to the sun, but Europa's ocean lies beneath tens of kilometers of ice. Sunlight never reaches it. So if life exists in Europa's ocean, it would have to get its energy from somewhere else. The leading candidate has always been the seafloor. On Earth, hydrothermal vents on the ocean floor support entire ecosystems that have nothing to do with sunlight. These vents occur where heat from inside the Earth drives hot, chemically rich water up through cracks in the rock and into the ocean. The organisms that live around them feed on chemical reactions rather than photosynthesis. If something similar were happening at the bottom of Europa's ocean, if there were active hydrothermal vents, fractures in the seafloor exposing fresh rock to seawater, volcanic activity driven by tidal heating, then the energy and chemistry for life could both be present. This is what many scientists hoped, and some models have suggested it is plausible. But in January 2026, a study led by researchers at Washington University in St. Louis reached a very different conclusion. Using calculations that accounted for Europa's size, the composition of its rocky interior, and the gravitational forces exerted by Jupiter, the team concluded that Europa's seafloor is most likely tectonically quiet. Not just quiet, possibly completely inert. The reasoning goes like this. Europa's core has had billions of years to cool. Any heat it originally contained would, by now, have largely dissipated. The heat that keeps Europa's ocean liquid comes primarily from tidal flexing, the squeezing and stretching of the moon's interior as it orbits Jupiter. This flexing is real. It is why Europa's ocean has not frozen. But the researchers calculated that the tidal stresses are not strong enough to drive significant geologic activity at the seafloor. They found that Jupiter's tidal forces on Europa's seafloor are currently only about 3% of the strength needed to cause fracturing in the rock, even in the most favorable conditions. Mantle convection, the slow movement of hot rock inside the moon, generates stresses that are more than 100 times too weak to drive tectonic activity. Global contraction from cooling, which can produce thrust faults, would require the rocky interior to have shrunk by a full kilometer to have any effect, and there is no evidence that has happened. If the seafloor is quiet, there are likely no active hydrothermal vents, no fresh rock being exposed to seawater, no ongoing chemical reactions to power a food chain. As the lead author put it, if you could explore that ocean with a remote control submarine, the prediction is that you would find nothing happening down there. Everything would be quiet. That is a sobering conclusion. But it is not the end of the story. Science rarely speaks with a single voice. And the question of Europa's habitability is one of the most actively contested areas in planetary science. While the Washington University study suggests the seafloor may be geologically inactive today, it also acknowledges that Europa may have been much more geologically active in its past, possibly substantially so. And a separate team of researchers, working with different models, published a study in 2021 suggesting that tidal heating could be sufficient to produce volcanic activity on the seafloor. The critical word is uncertainty. Europa's mantle viscosity, how easily the rock flows under heat and pressure, is unknown. The depth and distribution of tidal heating inside the moon are not precisely constrained. Different reasonable assumptions about these parameters produce very different conclusions. What the researchers at Woods Hole Oceanographic Institution added to the picture is also important. Even if the seafloor is not volcanically active today, they argue, lower temperature forms of fluid flow could still persist. On Earth, these so-called ridge flank circulation systems quietly cycle seawater through permeable rock at temperatures below 100 degrees Celsius. They support chemosynthetic ecosystems. They release nutrients and synthesize organic molecules. And they do not require active tectonics to function. The implication is this. Even a geologically quiet seafloor might not be a lifeless one if the right kind of low-temperature chemistry is occurring in the rock beneath it. The key question is whether Europa's interior is permeable enough and warm enough to sustain that kind of fluid flow. That question is not yet answered, and it is one of the things NASA's Europa Clipper mission is designed to investigate. While scientists debated the energy question, a separate line of research was quietly producing extraordinary results. They were finding things on Europa's surface that had no business being there if the ice shell was truly sealed and the ocean was truly isolated. In September 2023, two independent teams of researchers using data from NASA's James Webb Space Telescope published simultaneous findings in the journal Science. Both teams had been mapping the distribution of carbon dioxide on Europa's surface, and what they found was not what they expected. Carbon dioxide on an icy moon is not unusual. It can be deposited by meteor impacts. It can be produced by radiation chemistry on the surface itself. Neither of these sources would say anything interesting about what is in the ocean below. But the Webb telescope data showed something different. The carbon dioxide on Europa was concentrated in a specific region called Terra Regio, a geologically young area of disrupted terrain near the Moon's equator, where the surface ice has been broken apart and reformed. Previous observations had already shown this region contains ocean-derived salt. The concentration of carbon dioxide in the same region as ocean-derived salt pointed in one direction. The carbon almost certainly came from inside Europa. It came from the ocean. And it was deposited there on a geologically recent timescale. Carbon is a biologically essential element. It is one of the foundational building blocks of life as we know it. Finding a source of carbon inside Europa's ocean does not mean there is life in that ocean. But it is a critical piece of evidence. It means the ocean contains at least one of the key ingredients. One of the lead researchers summarized the significance directly. Carbon is a biologically essential element, she said. We now have observational evidence that the carbon we see on Europa's surface came from the ocean. That is not a trivial thing. Now, here's where it gets even more interesting. In January 2026, a separate team of researchers published a study revealing a completely different kind of detection from Europa's surface. Using reprocessed data from NASA's Galileo spacecraft data that was originally collected during a single observation in 1997 and had been sitting in archives ever since researcher Al Emran at NASA's Jet Propulsion Laboratory identified something hidden in the infrared spectrum: ammonia. More precisely, the spectral signature of ammonia-bearing compounds detected near fractures on Europa's frozen surface, specifically near the kinds of geological features that are associated with material rising from below. This was the first detection of nitrogen-bearing compounds on Europa, ever. The significance of this is hard to overstate. Nitrogen, alongside carbon, hydrogen, and oxygen, is one of the foundational elements of life as we know it. Its presence on Europa's surface, apparently delivered from the subsurface by cryovolcanic processes, adds another essential ingredient to the inventory. But the detection carries a second implication. Ammonia acts as a natural antifreeze. In sufficient quantities, it can lower the freezing point of water by as much as 100 degrees. The presence of ammonia-bearing compounds suggests that Europa's ocean may be chemically reduced, higher in pH, and because ammonia keeps water liquid at lower temperatures, perhaps covered by a thinner ice shell than previously thought. The data also suggests something about the timeline. Ammonia-bearing compounds are unstable in space. Jupiter's intense radiation environment destroys them relatively quickly within a timescale of less than 1 million years, which, in astronomical terms, is extremely recent. The fact that they are still detectable means they were placed on the surface recently. Something brought them up from below, not long ago. Even if the ocean contains the right chemistry, carbon, nitrogen, the building blocks of life, there is another problem. How do nutrients get into the ocean in the first place? Europa's surface is continuously bombarded by intense radiation from Jupiter. That radiation interacts with salts and water ice on the surface to create oxidants, molecules like oxygen and hydrogen peroxide that could, in principle, serve as chemical fuel for microbial life. The surface is, in a sense, a chemical factory. But that factory sits on top of tens of kilometers of ice. Getting those surface-produced chemicals down into the ocean requires a mechanism, something that can transport material from the surface all the way through the shell and into the water below. For a long time, scientists struggled to find a convincing explanation. Then, in January 2026, a research team from Washington State University proposed one. The idea was inspired not by planetary science, but by something that happens here on Earth. Deep in the planet's crust, a process called crustal delamination occurs when a section of dense rock becomes chemically enriched and heavy enough to detach from the crust above it and sink into the mantle below. The driving force is density. Heavy material falls. The researchers asked whether something similar could happen on Europa, and their computer models suggested that it could. Certain regions of Europa's ice surface are enriched in salts. Salt makes ice denser than the surrounding pure ice, and previous research had shown that impurities like salt weaken the crystalline structure of ice, making it less stable. If a patch of dense, salty, nutrient-rich ice becomes heavy enough and weak enough, the models suggest it can detach from the surrounding ice and sink, not quickly, but steadily, all the way down through the ice shell to the base and from there into the ocean. The process is relatively fast on geological timescales. It can repeat, and it works across a wide range of salt concentrations as long as there is at least some weakening of the surface ice. If this mechanism is real, it provides a steady and repeatable pathway for nutrients produced on Europa's radiation-blasted surface to reach the ocean below. The ingredients for life would not be locked on the surface. They would be slowly, continuously delivered to the water. These findings align directly with the scientific goals of NASA's Europa Clipper mission, which is scheduled to arrive at Jupiter in April 2030. Now we turn to something that was discovered not in space, but in a laboratory at the Open University in the United Kingdom. Inside a large vacuum chamber named George, large enough for a person to crawl into, which the lead researcher occasionally had to do, scientists placed 40 kilograms of water in a glass tank. Then they lowered the temperature and pressure to simulate the conditions on the surface of an icy moon. What they filmed inside that chamber changed how scientists think about Europa's surface. In space, when water erupts from a moon's subsurface onto the surface, it does not simply freeze. The pressure outside is so low, virtually a vacuum, that the water does something unexpected. It boils. And while it boils, thin crusts of ice form over the surface. The vapor pushes through those crusts, buckling them upward, separating them into layers. Then a second layer forms, and the vapor pushes through that one too. The result, observed clearly in the laboratory for the first time at this scale, is an ice structure that looks nothing like ordinary ice. The researchers described it as resembling phyllo dough, or a wasp's paper nest. Thin, fragile sheets of ice separated by gaps of vapor stacked in layers, with a porosity meaning the proportion of empty space of between 70 and 80%. On Earth, this structure grew to about 20 centimeters thick before its own weight suppressed the boiling. But Europa has much weaker gravity than Earth. In the lower gravity environment of Europa, the scientists calculated that similar structures could reach several meters in depth. On Saturn's moon Enceladus, where gravity is even weaker, the estimate rises to around 20 meters. This is not a minor engineering consideration. It is a potentially serious problem for any spacecraft that tries to land on Europa's surface near a region of cryovolcanic activity. The The fragile, layered ice which the researchers termed phylocellular ice would not support a lander. A spacecraft attempting to touch down on such terrain could punch straight through the crust and fall into the porous structure beneath. As one planetary scientist involved in the NASA Europa Clipper mission put it, if the surface is really covered with this type of highly porous, fragile water ice, that would definitely pose some serious engineering issues. The types of landing mechanisms previously proposed for Europa would need to be completely reconsidered. But the ice discovery carried a second implication, one that was perhaps more scientifically interesting than the engineering challenge. If this kind of fluffy, porous ice forms where water erupts onto Europa's surface, then that same porous structure should produce a distinctive radar signal. Europa Clipper carries radar instruments specifically designed to probe beneath the Moon's surface. The scientists proposed that the spacecraft should be able to detect fields of phylocellular ice from orbit, and that such detections would serve as markers pointing to sites where liquid water from below has recently reached the surface. In other words, the fluffy ice problem is also a map. It could show us where the ocean has been most recently active. The Juno measurement of the ice shell thickness deserves its own moment. For decades, the question of how thick Europa's ice shell is had been one of the most contested in planetary science. Some researchers argued for a thin shell, perhaps less than a kilometer in places, through which the ocean and surface could exchange material relatively easily. Others argued for a thick shell, tens of kilometers deep, which would act as an effective barrier between the surface and the ocean. The reason the question matters so much is habitability. A thin shell means easier exchange. Oxygen from the surface, produced by radiation chemistry, could make its way into the ocean. Nutrients could cycle between the two environments. The ocean would be more chemically active, more dynamic, more potentially habitable. A thick shell means the reverse. The surface and the ocean are largely isolated from each other. What chemistry happens in the ocean stays in the ocean. The nutrients and oxidants produced on the surface would have a much harder time getting down. When Juno flew past Europa in September 2022, coming within about 360 kilometers of the surface, its microwave radiometer measured the temperature of the ice at multiple depths across roughly half the Moon's surface. The result, published in December 2025 in Nature Astronomy, was a shell estimated at approximately 29 kilometers thick in the region observed. That is firmly in the thick shell camp. The researchers also noted that if the shell contains a slightly warmer, convective inner layer, which is possible the total thickness would be even greater, and if the shell contains dissolved salt, the estimate would be reduced by about 5 kilometers. The instrument also detected scatterers, cracks, pores, and voids in the ice just below the surface, extending to depths of hundreds of feet. These irregularities scatter radar signals in a characteristic way, but their small size and shallow depth suggest they are unlikely to be significant pathways for material to travel from the surface down to the ocean. A thick, largely impermeable shell is not good news for the idea of easy surface-to-ocean exchange. It places greater importance on the internal mechanisms, the delamination process, the cryovolcanism, the seafloor chemistry, as the primary drivers of whatever habitability might exist in the ocean below. Now step back and look at everything together. Here is what the data from various missions and studies suggests. As of today, Europa has a global saltwater ocean. That is not seriously disputed. The magnetic measurements from the Galileo spacecraft established this with high confidence. That ocean sits beneath an ice shell approximately 29 kilometers thick in at least some regions. It is possibly even thicker elsewhere. The shell is largely impermeable to downward transport of surface materials, though mechanisms like ice delamination may offer some pathways. The ocean itself contains carbon derived internally. This was established by the James Webb Space Telescope in 2023 from the distribution of carbon dioxide in geologically young terrain. The ocean also contains nitrogen-bearing compounds, most likely ammonia hydrate and ammonium chloride, detected in data from the Galileo spacecraft collected in 1997 and reanalyzed in 2026. These materials are unstable in space, suggesting they were recently deposited on the surface from below. The surface ice, in regions of cryovolcanic activity, may be extraordinarily fragile, layered, porous, and potentially meters deep in some locations. The seafloor may be geologically quiet, with limited tectonic activity and no confirmed active hydrothermal vents, but low-temperature fluid flow through permeable rock, similar to ridge flank circulation on Earth, could still be occurring. A mechanism exists inspired by Earth's crustal delamination, by which nutrient-rich surface ice could sink through the shell and deliver its chemical contents to the ocean over geological timescales. So here is where we stand. Europa has the right ingredients: carbon, nitrogen, liquid water, possibly some energy input, possibly some mechanism for cycling nutrients. But the energy question remains open. The seafloor question remains open, and the question of how effectively the surface and ocean communicate remains open. Every piece of evidence we gather answers one question and opens three more. That is not a failure of science. That is what science looks like when it is working. The next chapter of this story will be written by a spacecraft currently traveling through the outer solar system. NASA's Europa Clipper launched in October 2024. It is on its way to Jupiter now. It is scheduled to arrive at the Jupiter system in April 2030. Europa Clipper will not land on Europa. It will orbit Jupiter and perform dozens of close flybys of Europa, some coming within just 25 kilometers of the surface. Each flyby will be fast, but the spacecraft carries 9 scientific instruments, and each one is designed to answer a specific set of questions. Its radar instruments will probe beneath the ice, measuring the shell's thickness and structure, searching for subsurface lakes, looking for signatures of porous, fluffy ice that would indicate recent cryovolcanic activity. Its spectrometers will map the composition of the surface in far greater detail than Galileo or any other previous mission, potentially identifying more compounds that originated in the ocean below. Its magnetometers will take new measurements of Europa's induced magnetic field, which will help constrain the depth and salinity of the ocean. Its cameras will image the surface at resolutions that will allow scientists to map geological features in ways that were simply not possible before. And if any plumes of water vapor are erupting from the surface, something that has been tentatively observed but never confirmed, Clipper will fly directly through them, tasting the ocean from above. The question of whether Europa's seafloor is geologically active is one that Europa Clipper is specifically designed to help answer. The question of whether the surface and the ocean exchange material and how is another. The question of whether ammonia-bearing compounds are widespread across Europa's surface or confined to a small region is a third. The researchers who found the fluffy ice problem are already planning for Clipper's arrival. They have identified the radar signatures that would distinguish phylocellular ice from ordinary compact ice, and they have proposed analysis methods to map its distribution across the surface. The researchers who found ammonia in the Galileo data have called explicitly for Clipper to extend the search to other regions of the Moon, using instruments far more sensitive than anything Galileo carried. The team who proposed ice delamination as a nutrient delivery mechanism intends to use Clipper's measurements of the ice shell's structure and composition to test their model directly. Everything is pointing toward 2030. It is worth pausing to think about the scale of what we are discussing. There is a moon in orbit around Jupiter. It is slightly smaller than our own moon. You could hold it in your mind as a single, compact object smaller than many countries on Earth. And inside that object, there is a liquid ocean that contains more water than every ocean on this planet. In that ocean, There is carbon from an internal source. There is nitrogen, probably delivered by the same internal processes that create the moon's fractured surface. There is salt, and there is chemistry that we are only beginning to understand. Above it, there is a shell of ice that is being constantly rearranged by the tidal forces of a planet 11 times the size of Earth. Whether life exists there depends on questions we cannot yet fully answer. Whether there is enough heat at the seafloor, whether nutrients cycle efficiently enough between the surface and the ocean, whether the chemistry of the ocean provides the right conditions for the kind of metabolic reactions that, on Earth, gave rise to everything alive. Some studies say the seafloor is quiet. Others say it may have been active in the past, and the remnants of that activity could still matter today. Still others say that even a quiet seafloor, with the right kind of low-temperature fluid chemistry, could sustain life at modest levels. What the data actually says is this: the ingredients are present, the water is there, the carbon is there, the nitrogen is there, the mechanism to deliver nutrients exists. Whether the energy is there in the right form, in the right place, at the right time, remains the central unanswered question. And what the laboratory says is this: the ice on Europa's surface, where it has been most recently active, may be fragile enough to collapse under the weight of a lander. The ocean worlds of the outer solar system are not the simple, frozen places they once appeared to be. They are dynamic, chemically rich environments, and we are only beginning to understand them. For now, Europa waits. It has been orbiting Jupiter for 4.5 billion years. The ice cracks and reforms, the ocean churns, or perhaps sits still. Material rises from below and is deposited on the surface, where it is slowly destroyed by radiation, only to be replaced by more material from below. In a few years, a spacecraft will fly through whatever is erupting from that surface and measure what it finds. It will look at the ice with radar. It will map the chemistry. It will measure the magnetism of the ocean beneath, and then we will know more than we do today. That is, perhaps, the truest thing that can be said about Europa. We are getting closer. Every measurement brings us closer. And the closer we get, the more remarkable the picture becomes, not because we are finding what we expected, but because we keep finding things we did not expect at all. A nitrogen-bearing compound hiding in data from 1997, waiting nearly 30 years to be found. A mechanism for delivering nutrients to a subsurface ocean borrowed from the geology of our own planet. A type of ice that nobody had ever seen before, discovered in a vacuum chamber with a fish tank. An ocean floor that may be the quietest, most still place in the entire solar system. None of it was predicted. All of it is real. And somewhere beneath 29 kilometers of ice, in an ocean that holds twice the water of all Earth's seas, the chemistry that began when this solar system was young is still happening. Whether it ever produced anything that could be called life, that is the question. For now, all we can do is watch and wait, and send one more spacecraft to take a closer look. What we know so far is remarkable enough. What we don't yet know may be even more so.